This is a maglev train project I made at college at Wesleyan University in May 2018, although it's now 2026 as I record this video. Maglev stands for magnetic levitation and is used in high-speed trains where the train floats above the track to avoid the limitations that come with wheels rolling on rails at high speeds. Large-scale systems are built with very different methods and constraints than my small-scale design, so my project is not meant to be a direct replica of a real maglev train.
Yeah, we'll make it go backwards.
For this project, I brainstormed my own small-scale maglev train and track design in Adobe Illustrator and laser cut the parts. I also used magnet wire to create the coils and soft iron rods as the cores. I used an Arduino to control the logic for moving the train. My total cost was around $600 in materials. For the vertical hover, I put neodymium magnets on the length of the track and also in the side wings of the train. I relied on friction to keep the train aligned horizontally in the track. Later, I added bottom magnets to the wings to stabilize the vertical position and reduce bouncing. And I also added bearings to the sides to reduce the friction still present in maintaining horizontal positioning. The forward and backward movement involves permanent magnets on the track and electromagnets on the train that can be turned on or off at certain intervals. A stronger electromagnet can be achieved by using a soft iron core in the center, adding more turns of wire to the coil, or increasing the electric current sent through the wire. There are trade-offs though, because more turns can also add more resistance, and smaller diameter wire can handle less current before overheating. So I had to estimate the magnet wire diameter and the number of turns to use. Then I used a resistance meter to gauge what battery voltage I could use to maximize the electromagnet strength while staying under the wire's current limitations, using the formula V equals IR, where voltage equals current times resistance. The electromagnet can be turned on or off by sending electricity through the coil, and the north and south ends of the electromagnet can be reversed depending on which direction the current flows through the wire. I offset the electromagnets with the position of the permanent magnets on the track, so that electromagnets 1 and 3 would pull together from the optimal position, while 2 and 4 sat idle until moving into their optimal position. Then the pairs would alternate being active repeatedly. The Arduino knew the train's position on the track by using a Hall effect sensor at the front of the train, which measured the magnetic field emitted by the track. I'm very pleased with how the maglev train project turned out. And hey, I didn't burn the science building down as I snuck in to use the laser cutter several late nights.
No?
Putting your face like this?
That's weird, no.
That's weird?
Yeah, that's weird. What do you mean?
So, just so you're aware, it took